Section 9 is an introduction to FRAM. FRAM, or Ferroelectric Random Access Memory, is an exciting new technology that Texas Instruments is beginning to use in the MSP430 product line. Even though it's not currently used in the Value Line series, you should be aware of its potential for future design opportunities.
FRAM is a new technology memory being worked on with Texas Instruments. Although these are not currently available in Value Line parts, I thought it was important to give you a flavor for what's coming in the future in this exciting new memory technology. So why is there a need for a new memory technology? In the 21st century, the things that we see happening are many things are going wireless, low power is a concern, security is a concern. We need to drive new applications into networking. Things like energy harvesting, for example, that are devices that are all networked to get together. We want to improve the time to market and lower the total cost of ownership by creating something like a universal memory. So what are the requirements for a new memory technology? We would want very low power consumption. We want fast access speeds. We want high write endurance. We want high inherent security on them. And we want a lower goes with it. FRAM technology attributes match directly with the things that I just talked about. FRAM is non-volatile. It retains its data without power. It has fast writes and updates with RAM-like performance. Up to about 50 nanosecond per byte access times today. That's more than 1,000 times faster than Flash or EEPROM. Low power. It needs 1.5 volts to write, compared to a Flash or EEPROM that requires 10 to 14 volts to actually write to a cell. That means there's no charge pump required on the device. Superior data reliability. A write guarantee in case of power loss, that I'll talk about more in just a second, and greater than 100 trillion read and write cycles that have been tested on these devices. So what kind of target applications will FRAM devices fit in? Things like data logging or remote sensor applications, things that require high write and write cycles. Battery-powered consumer and mobile electronics, devices that have low power requirements. Energy harvesting, especially wireless, things that need low power and fast memory access, especially writing to the device. Battery-backed SRAM replacement, non-volatility, high write endurance, low power, fast writes, all of those are things that you can see happening with FRAM. A single FRAM cell can be considered a dipole capacitor that consists of a film of ferroelectric crystal between two electrode plates. Even though the term is ferroelectric, there's no iron material involved. Writing to FRAM requires polarizing the crystal in a specific direction using an electric field. This makes the FRAM very fast, easy to write to, and capable of meeting high endurance requirements. Reading from the FRAM requires applying an electric field across the capacitor similar to a write. Depending on the state of the crystal, it may get repolarized and emit a large induced charge. That charge is then compared to a known reference to estimate the state of the crystal. The stored 1 or 0 is inferred from the induced charge. In the process of reading the data, the crystal that's polarized in the direction of the applied field loses its current state. Hence, every read needs to be accompanied by a write back to restore the state of the memory location. This is inherent to the nature of the FRAM memory and is completely transparent to you, the end user. If we take a look at all the different memory technologies that you can have in a microcontroller, FRAM, SRAM, EEPROM, and Flash, out of those, only the FRAM has all of the capabilities that you're looking for. Non-volatility, write speeds, high write speeds, low average power, high write endurance, bitwise programmability, but only the FRAM has the ability to be unified memory, so that you can flexibly partition code and data, that you only have to buy a single type of device, that you can decide whether or not you're using part of it as SRAM or part of it as flash. No, you want to move that differently. You only have to buy a single part. So if we look at the details here, non-volatility, of course, SRAM does not have that. Write speeds for FRAM down in the 10 millisecond range. Average active power down in the 110 microamp per megahertz. Write endurance 100 trillion plus. Wise program, unified memory inside there. This is a look at the FRAM controller. The functions of the FRAM controller: the RAM reads and writes just like standard RAM, but the read-write frequency has to top out at about 8 megahertz. If you have an M clock greater than 8 megahertz, then you're going to activate wait states, and that can be either manual or automatic. Included in the current FRAM controller is a seamless and transparent integrated cache. That cache allows you to access small loops, gives you greater speed, greater flexibility, while not touching the FRAM at every single cycle. Error checking and correction is built directly into the FRAM read and write cycle. TI's FRAM devices have a built-in two-way forward cache that's transparent to the user and always enabled. The cache helps by lowering power by executing from SRAM. If you take a look at the diagram at the bottom, you can see for a 0% cache hit, which is the purplish line on the top, that would be if we didn't have a cache at all. So that's the active power microamps versus the M clock megahertz down there, going all the way down to a full-on RAM 100% cache hit down at the bottom. A typical would be right there about the center, the 66% cache hit. You can see it's still significantly lower in power per megahertz than if you didn't have a cache. The cache also increases the throughput by overcoming the 8 megahertz limit on FRAM accesses, and it can increase the endurance, specifically for frequently accessed locations and very short loops. I mentioned before the concept of unified memory. Before we had FRAM, you would have to buy multiple device variants. For instance, the top is a 16K program, a 2K SRAM. Let's say you needed double EEPROM in that device, so you often had to add an additional 1K double EEPROM on there. If you needed, in the bottom down there, if you needed more SRAM, you needed additional SRAM, you had to together. One device can support multiple options, so you can slide that bar back and forth as you need to. The data versus program memory can be partitioned as you need to partition it. So for multiple designs, multiple uses, you can have a single device. That gives you easier and simpler inventory management, lower cost of ownership, and a faster time to market for memory modifications because you have a single device. Current MSP430 FRAM devices have the FRAM with the cache in them, and they also have a certain amount of RAM inside. So you can determine where you put completely in FRAM or completely in SRAM as a case study here. In the first case, all your global variables might be assigned to FRAM. The advantage, of course, all your variables are non-volatile. There's no special handling required for backing up specific data. The disadvantage is, of course, that starts to use up code space. It can increase your power and decrease your throughput if you have the CPU running at greater than 8 megahertz. In the other case, you might put all your global variables in SRAM. The advantage would be some of the variables may need to be volatile, like in a state machine, or frequently used variables that don't cause a throughput or power impact. The disadvantage: the user has to explicitly define the segments to place those variables into the FRAM. Now, achieving a optimized user experience and exactly what you want to do, that's a work in progress. We're still learning right along with you. Unlike most MSP430s, the FRAM series of parts have a memory protection unit. The FRAM is so easy to write to that both the code and your non-volatile data need protection. So the memory protection unit can protect against accidental writes, read, write, and execute by executing read, write, and execute only permissions. So you can configure main memory in 3 variably sized segments and allow. So you can allow, in each one, you can allow either read or write or execute only inside those. The MPU registers, the memory protection unit registers, are password protected, so you don't have to worry about them getting changed. Any violation of the of those constraints, the access rights, would generate a fault and give you and put you into your fault handler. To maximize the speed of FRAM writes, those write speeds are mainly limited by the communication protocol or the data handling overhead rather than the FRAM itself. For in-system writes, the FRAM can be written to as fast as 16 megabytes per second. The write speed is directly dependent on whether or not you're using the DMA, the system speed, and the block size. You can see in the graph below the megabytes per second versus the number of bytes in a single block transfer down there. It all basically tops out at around 16 megabytes per second. Let's look at a case study for FRAM ultra-fast writes. In this and the next couple of cases, we're going to be using the same parts and comparing them one against the other. We'll use the MSP430 FR5739, which is a FRAM type part, versus the MSP430 F2274, which is a flash type part. Both devices are going to use the same system clock at 8 megahertz. The maximum write speed on the FRAM is 1.4 megabytes per second. That's more than 100 times faster than the maximum speed of writes to the flash at 13 kilobytes per second. Again with the same 2 parts. Let's look at low active write duty cycle. Both devices write to either FRAM or flash, non-volatile memory, at 13 kilobytes per second. The FRAM remains in standby for more than 99% of the time because it's so much faster. The power savings is greater than 200 times that of flash. You can see we're using 9 microamps as we're writing to the FRAM versus 2,200 microamps when we're writing to the flash, both of those when we're writing at 13 kilobytes per second. Let's take a look at the ultra-low power capabilities of FRAM. Using the same 2 parts, the average power for FRAM, 720 microamps, writing at 1,400 kilobytes per second. Average power in the flash, 2,200 microamps, writing at 13 kilobytes per second. So it's 100 times faster using half the power. That enables you to use more unique energy sources. For example, energy harvesting via vibration, via heat, via solar. The FRAM also implements non-blocking writes. The CPU is not held up and interrupts are allowed during the programming. The FRAM has increased flexibility. One thing that a lot of designers don't take into account is if you're doing in-system writes of flash or double EEPROM, for example, you have to implement some kind of backup procedure on power fail. Storage capacitor outside the device so that you would be able to write the last few writes while you're understanding that you've lost power. The FRAM has built-in circuitry to complete the current 4-word write. That's completely supported by the internal FRAM low dropout regulator and the capacitor. so that the in-system backup is an order of magnitude faster with FRAM than you could do with double EEPROM. As far as endurance goes, again using the same two parts. The FRAM endurance is greater than 100 trillion writes. Flash endurance is typically around 100,000. So as a comparison, you might write to a 512 byte memory block at a speed of 12 kilobytes per second, a fairly reasonable thing to do. If you were to do that in that same block with Flash, you'd be able to write 100,000 times in about 6 minutes, which would use up that Flash. For FRAM, it would take over 100 years. In fact, a lot more than 100 years in order to make that, in order to do that. FRAM devices are somewhat susceptible to higher temperatures. TI factory programming is not available for FRAM devices. You should program the devices after reflow. Documentation followed when you're doing reflow soldering activity to the board. Hand soldering is not recommended because you can concentrate so much heat on the part. However, it can be done by following the next couple of guidelines. Be mindful of the temperature. The FRAM can be affected above 260 degrees C for long periods of time. If you use a socket on an evaluation board during prototyping and you're doing a lot of soldering, that's probably a best practice as well. So to wrap up the FRAM section, FRAM's proven and reliable. Endurance, the proven data retention is 10 years at 85 degrees C. It's less vulnerable to attacks, fast access and write times. Radiation resistance, the terrestrial soft error rate, is below detection limits, and it's immune to magnetic fields. The FRAM does not contain any iron. For additional information on TI's FRAM technology, go to www.ti.com/FRAM.
This completes the main part of the workshop. The workshop material also contains a section and 3 labs covering capacitive touch. If you're motivated to do so, purchase the Capacitive Touch Booster Pack and go through that material. Thanks for staying with us through the videos. Good luck with your Texas Instruments MSP430 projects.